All right, so let's get started. So kind of the remainder of this course is dedicated to the topic of structures in chemistry, molecular structures, which I think is a very fun topic, not too terribly stressful. All right, we do need to review some old things, some old concepts that we're going to need to know in order to do this chapter correctly. The first one are valence electrons. Alright, so valence electrons are called the outermost electrons. So I'm putting in quotes here because they are physically the most distant from the center of the nuclide, but really what we mean by outermost is the highest energy electrons. All right, and an atom's valence electrons are super important because these are the electrons that participate in chemical bonding. All right, so if we're going to start talking about molecules here, we need to be able to first talk about how many valence electrons each atom is bringing with them to form that molecule. All right, we have a very easy way to do this by looking at the periodic table. Okay, every element that lives in that first column on the periodic table has one valence electron. All right, everybody that lives in the second column has two valence electrons. All right, those are the electrons those metals are losing to become cations. We're going to go ahead and skip over our transition metals. And it just continues to go in order. Everything in boron's column has 3 valence electrons. All right, so given this trend, what do we think about carbon's column? 4 valence electrons. Nitrogen's 5. 6 for oxygens. 7 for our halogens. And then 8 electrons for our noble gases. All right, there is one exception here. Which one of these noble gases is kind of living in the wrong column? The helium, right? Helium's so teeny tiny, it really should kind of be over here with only 2 valence electrons. All right, but we like to keep it with the noble gases because it behaves like a noble gas. It doesn't form any compounds. Cool. All right, so this is going to be important. Basically, we're going to need to total up the number of valence electrons that we have in a given molecule. All right, actually, let's just practice that. So, given a formula like CH4, I need to know the total number of valence electrons that are in this molecule here. All right? How many are each of these atoms bringing to the game? So each carbon, this one carbon actually, is going to bring how many valence electrons? 4, because that's where carbon lives on our periodic table. All right? And then I'm going to add 4 times the number of valence electrons that each hydrogen has. And how many valence electrons does each hydrogen have? Just 1. So this gives me a total of 8 valence electrons in this compound here. All right, and to be clear, why did I multiply that number of valence of electrons by 4 for hydrogen? Because there's 4 of them in my compound. Cool. All right, awesome. So next step here, we need to talk about what's called the octet rule. All right, and so when we're talking about the octet rule helps us answer kind of an important question here, which is why do atoms form bonds in the first place? Right? Why aren't they all just independently floating around? Why are they bothering to form these bonds between them? All right? So, every atom wants to do one thing, has one goal in mind, and that is to fill what's called its valence shell. All right? So the reason why they start sharing electrons with one another is so that they can get to this full valence shell. So why do atoms form bonds? To fill their valence shell. All right, and why do we call it the octet rule? Because most elements need 8 electrons to fill that valence shell. So we call it the octet rule because most elements on that periodic table want 8 electrons in order to fill their valence shell. All right? But of course, I got this caveat word in there, most. So there are some exceptions to this rule. All right, hydrogen as well as helium are both so teeny tiny they only have 1 s orbitals, so they can only fit 2 electrons into their valence shells. All right, helium you're never going to have to worry about because helium's a noble gas, it doesn't form compounds, but hydrogen, this is a really important exception to keep in mind, right? Every hydrogen atom just wants 2 electrons to fill its valence shell. All right, we continue sort of going through the teeny tinier elements here. Beryllium needs 4 electrons to fill its valence shell. All right, whereas boron needs 6 electrons to fill its valence shell. All right, so we call it the octet rule, which is kind of a misnomer for certain elements. It works for most elements. Most elements need 8 electrons to fill their valence shells. Some elements, though, have this sort of small exception here. All right. One other thing that we're going to see in this class that you wouldn't have seen in your previous semester in Chem1AFA is we're also going to talk about the expanded octet rule. Okay, it turns out that some elements, as long as they're pretty big in size, they can accommodate up to 12 electrons in their valence shell, but they have to be relatively large elements. All right, so you're only going to see this for elements that live in rows 3 and below. All right, so our expanded octet rule is elements in row 3 or more may have 10 valence electrons or 12 valence electrons. They don't have to. They may have 10 or 12. All right, a good example is sulfur. Sulfur lives in row 3 on the periodic table, so it can have one of these expanded octets. There are compounds where sulfur only has 8 electrons in its octet, or in its valence shell. There are other compounds where it has 10, and other compounds where it has 12, right? So it may have 10 or 12, as long as it's big enough, as long as it lives in row 3 or below. Cool. All right, so where we're going to start in our discussion of structures is what is called the Lewis structure of a molecule. All right. We've taken a look at a few Lewis structures. These are 2D representations of molecules. All right, importantly, your Lewis structure gives you 2 important pieces of information. Who is bonded to who? All right, where are the covalent bonds in your molecule? Which two atoms are bound together in that molecule? All right, as well as where the electrons live in a molecule. All right. Importantly, these are 2D representations of molecules, which are in fact three-dimensional objects, right? So they're not exactly a perfect descriptor of the shape of that molecule. All right, we will talk about shape, but we're not there when we're doing Lewis structures. So importantly, the orientation of your atoms does not matter. All right, I'll sort of give an example of what I mean by this in a second. Let's remind ourselves we've looked at these Lewis structures before. So for example, water was HOH, and it had these two lone pairs on that oxygen. All right. What were the lines in my Lewis structure? What did these ones represent? These are my covalent bonds. All right, and how many electrons make up one of those covalent bonds? 2. And then we also have these dots here. What did we call the dots? Lone pairs. All right, and each pair of dots is also 2 electrons. Okay, so looking at this water molecule here, what are the total number of electrons that we see on the board here? 8. So we got 2 for this covalent bond, 4 for this one, 6 for that lone pair, and 8 for that lone pair. Okay, so we can count the number of electron pairs we see in our Lewis structures. All right, so let me just copy this over real quick. What do I mean by that last portion when I said that the orientation doesn't matter? Well, here I have my oxygen and my hydrogens kind of drawn all in a straight line here, right? I could have put those hydrogens anywhere around that central oxygen. So for example, I could have put one over here and one down here. This is also a perfectly fine Lewis structure for water, all right? Because in both of these, I show that my hydrogen is covalently bound to that oxygen in the middle, and I show that that oxygen has 2 lone pairs, right? So I show who's bonded to who and where the electrons live in this molecule. All right, so importantly, these are the same. Doesn't matter. Cool. All right, so let's talk about how we draw Lewis structures. All right, and we're going to use that same CH4 example to do it here. All right, so step 1 is what we already did. We're going to total the number of valence electrons. All right, so that's what we did before when we were looking at our periodic table, and we said, all right, carbon has 4 valence electrons, and each of those 4 hydrogens have 1. So when I sum that all up, I get a total of 8 valence electrons. All right, and we're going to note this over to the side here, because this is going to be important. This is the total number of electrons that we should have in our structure when we get done drawing our Lewis structure. No more, no less. All right. So now we're going to place our central atom in the middle of this Lewis structure. All right, and importantly, which one of these is going to be my central atom? All right. You can usually tell by the formula it's usually the first one listed, but that's not always the case, as is with water, right? So it's the least electronegative element. With the exception of hydrogen, which is never the central atom. All right, so I'm going to do my work over here. Okay, and I'm going to put that carbon in the middle. Boom, there's my central atom. And now I'm going to decorate the outside with those what we call constituent atoms. All right, so place those remaining constituent atoms around the central atom. Okay, so I got to place these 4 hydrogens, right? So I'm just going to kind of go clockwise here. 1, 2, 3, 4. All right, all I did was put them all around, decorate that central atom with those 4 constituent atoms. Okay, and up until this point, we haven't put down any electrons in our structure now. But now we're going to connect the central atom and the constituent atoms with single bonds. All right, so I have my central atom and these 4 hydrogens around it. I'm just going to draw single covalent bonds connecting everything to the middle. All right, and now I actually have some electrons down on the board here. All right, what each one of those sticks represents how many electrons? 2. So for each covalent bond, I'm going to need to deduct 2 electrons from my total. Remember, I'm only supposed to have 8 on here at the end of the day. So for each one of those covalent bonds, I need to subtract 2. I got 4 of them, so 2, 4, 6, 8. So I have no more electrons here. All right, so for each bond, subtract 2 electrons. All right. The last step that we're going to do, we don't have any more electrons left over. I'm going to leave some space right here, though, because I'm going to complicate things here in a second. But we have always the same last step, which is to ask ourselves, is everybody happy? And what do I mean by happy? Complete octet, right? That complete valence shell. All right, so once we get done laying down all of our electrons, we got to go back to our structure and double check, okay? This hydrogen atom right here wants to have how many electrons to fill its valence shell? 2. All right, cool. And how many electrons are in each one of those covalent bonds? 2. So this guy right here, because it's shared, that pair of electrons has a full valence shell. So this thing's happy. Check, check. all right? In fact, all hydrogens just want to have one covalent bond, right? This one also has two, and this one has two, and this one has two. So all of my hydrogens are indeed happy. And what about carbon in the middle? How many electrons does carbon want to have? Carbon's a normal, not a big one, right? Just a normal old element that wants to have 8 for its octet rule. And again, each one of these bonds is 2. So that's 2, 4, 6, 8. Right? So everybody here is happy. We're good with this structure here. All right? So this is my structure, my Lewis structure for CH4. Cool. All right, so we left some room here because once we added all of those bonds, we were already through all that pool of 8 electrons that we had. So now let's say if there are electrons left over, what do we do? Okay, yep, so we're going to make them lone pairs. But where are we going to put those lone pairs? We're going to have one particular strategy where the first thing we do is make everybody on the outside happy. All right, so we're going to complete the octet of all of the constituent atoms first, and then if anything's left over, we put them on the central atom. All right, so we're going to add lone pairs. First, add lone pairs. To complete the octet of the constituent atoms. All right, then if anything's left over, add those remaining electrons to the central atom. All right, so here are our rules for drawing these Lewis structures. Okay, put the central atom, the least electronegative element in the center. Everything else you're going to decorate around it. All right, you're going to connect everything to that central atom with single bonds. For every single bond, you're going to subtract 2 from your total. All right, if you have anything left over, you're first going to make the outside elements happy, and then you'll put anything that remains on the central atom. Cool. All right, so let's do some examples here. All right, given our rules, I'm going to give you these formulas, and I want you to see if you all can give me the Lewis structures. So carbon tetrachloride, NH3 is ammonia, and then we're going to do oxygen difluoride. All right, so given these 3 chemical formulas here, see if you can't get me the Lewis structure of these molecules. All right, let's do this. So CCl4 has 32 valence electrons, right? Carbon has 4, each chlorine has 7. So that's 28 for the 4 chlorines plus the 4. So I think my math, yeah, okay. So I'm going to put the less electronegative element, the carbon, in the center, and I'm going to put all the chlorines around it, right? And what am I going to do next? Draw bonds. So I'm just going to put single bonds here between that central atom and everything else on the outside. And how many electrons did I just lay down? 8. So I need to subtract that from my total up here. All right, what was that, 24? Cool, so I got 24 electrons that remain. These need to go on the board before I'm done, right? So what do we say? The first thing that we're going to do with these leftover electrons is put them on which element? The constituent, right? So the chlorines. I'm going to put them on the outside first. And chlorine wants to have how many electrons to fill its octet? 8. It's a normal old octet rule element, right? It has 7 valence electrons when that's what it like brings to the table, but it wants a total of 8 to have a full valence shell. So currently, as drawn, this chlorine only has 2. So in order to complete its octet, I'm going to need to add another 3, 4, 5, 6, 7, 8, or 3 lone pairs to make that chlorine happy. Right, and I can just keep on going around. Same thing up here. This chlorine is going to need 3 lone pairs. This chlorine is going to need 3 lone pairs. And this chlorine is going to need 3 lone pairs. All right, so if I put down 6 electrons on these 4 chlorines, that means I just laid down another 24 electrons. All right, so now we just got to make sure to double check that everybody's happy. Everybody's got a complete valence shell. All right, well, my chlorines better be happy. That's why I gave them those 3 lone pairs, right? So here's 2, 4, 6, 8. You can convince yourself that all 4 chlorines are in the same boat. And then what about that carbon? How many electrons are in its valence shell right now? Also 8. 2, 4, 6, 8. So is everybody happy? Yeah, cool. So here we go. This is our structure for carbon tetrafluoride. All right, we're going to play the same game now, but now we have a new formula here, NH3. So I went through and I totaled up the number of valence electrons, and I got 8. I'm going to put that nitrogen in the middle and the hydrogens on the outside, and I'm going to draw covalent bonds to connect them. All right, so how many electrons did I just lay down? 6. So I got 2 left over. Okay? I need to make the constituent atoms happy first, the hydrogens happy first. How many lone pairs should I put on each of those hydrogens? Yeah, trick question. They're already happy, right? They already got their full valence shell, which is 2 electrons. I still got these 2 that I got to put down. And since everybody's on the outside is happy, where are those 2 going to go? In the middle. Boom. All right. So now I need to make sure that everybody's happy in this compound here. Each hydrogen has its 2, so they are happy. And my nitrogen has 2, 4, 6 in covalent bonds, but that lone pair brings it up to a total of 8. So my nitrogen is also happy. Whoops, I'll do that. All right. So my last one here, my oxygen difluoride. My oxygen's less electronegative than fluorine, so that's going to go in the middle. I got a total of 20 electrons to work with. I'm going to connect everything with single bonds. All right, that's 4. So now I have 16 left over. Those electrons are going to go where first? The oxygen or the fluorines? Fluorines, the ones on the outside. So each fluorine is going to want 1, 2, 3, 4, 5, 6 more electrons to complete its octet. Cool. So that's 12. All right, but I still got 4 left over. Where are those 4 supposed to go? On the central atom. So 1, 2, 3, 4. And again, we need to double check that everybody is happy. Fluorine, 2, 4, 6, 8. So that's happy. 2, 4, 6, 8. Same with that one. And then my oxygen also has 2, 4 in covalent bonds, and then 6, 8 in lone pairs. Cool? All right. So we got this set of rules that we're going to apply. We're going to complicate things a little bit here. You're going to do 2 more for me based on what we just did. All right, the first one is SF4, sulfur tetrafluoride. And the other one is what's called formaldehyde, CH2O. All right, so let's go through it here. This middle one's a little bit tricky. All right. For this sulfur tetrafluoride, I totaled up my valence electrons and I have 34. I'm going to draw those single bonds to that central atom. All right. If I draw those 4 bonds, just lay down 8. So I got 26 left over. And those 26 are first going to go on which element? Sulfur or fluorine? Fluorine, the outside first. And just like before, we're going to need to put 3 lone pairs on there to complete the octet of each of these fluorines. All right, so that's 6, 12, 18, 24. And now I have 2 electrons. Where do I put those remaining electrons? On that central atom. All right? So, now let's ask ourselves, is everybody happy? So the fluorines, are the fluorines happy? Yes, they have their 8 electrons. And what about sulfur? How many electrons does sulfur have in its valence shell right here? 10. It's got 2, 4, 6, 8. But that lone pair makes 10. Is that allowed? Yes, right? Okay, we have this new expanded octet rule. Remember, as long as an element is in row 3 or greater, it may have 10 or 12 valence electrons. All right, we have an expanded octet rule. As long as you're big enough, as long as you're row 3 or down on the periodic table, you can have that expanded octet. All right, so here's just an example. Let me get rid of my little orange markings. Okay, but here is a good example of a compound with one of those expanded octets. All right, cool. So now let's go to this one, formaldehyde. We have 12 valence electrons to work with. I put my carbon in the middle, my hydrogens and my oxygens on the outside. All right, remember the orientation doesn't matter. I could have a hydrogen over here or an oxygen over here, or these could be swapped. It doesn't matter, all right? I like it the way I had it though, so I'm gonna put it back. All right, I'm gonna draw single bonds to that central atom. Okay, that was a total of 6. So I got 6 more. All right, where are those 6 gonna go? Which element? Oxygen, my constituent first. That completes oxygen's valence shell, leaving me with 0. All right, so is the hydrogen in this molecule happy? Is the oxygen in this molecule happy? Cool, and is the carbon in this molecule happy? No, my carbon only has 1, 2, 4, 6 electrons in its valence shell. All right, and what you cannot do is just say, all right, well, I'm going to put 2 more in there. No, no, no. You only had a total of 12 to work with. 12 electrons is all that's allowed to be on the board here. All right? So what are we supposed to do? We can't add any more electrons. What we're going to have to do is rearrange what's already on the board here. All right? What do I mean by that? I'm going to take this lone pair right here, this lone pair on this oxygen, and I'm going to bring it down and turn it into a bonding pair of electrons. Right? Now it's associated not just with the oxygen atom, but with the carbon as well. Right? By making it from a lone pair into a bond, now both of those atoms get to count that pair of electrons towards their octet. All right, so we have to add one more thing to our little list of rules here. Right? We said we were going to check and ask if everybody was happy, and up until now, everybody's always been happy. So what are we supposed to do if somebody's not happy? Okay, we're going to rearrange the electrons on the page by converting lone pairs to bonds, or if you've gone too far, maybe you need to do vice versa. Alright, so I followed all my rules up until now. Alright, and again, this is where that left me. And I said, alright, well, is everybody happy? And the answer was no, carbon's not happy. So I'm going to rearrange what's already on the board. I'm going to take a lone pair from the oxygen and turn it into a bonding pair. And now if I count my oxygen's octet, it's got 2, 4, 6, 8. And if I count carbon's octet, it has 2, 4, 6, 8. Okay? Cool. So then one more for me for the sake of practice here. You're going to give me HCN. All right. For the sake of time, I will tell you that there are 10 valence electrons in hydrogen cyanide here. I put that carbon down in the middle, decorate it with the constituents on the outside, and then draw those single bonds. I got 6 left over. I'm going to make everybody on the outside happy first. Hydrogen's already happy. So I'm going to make my nitrogen happy. All right. And that gets rid of all 6 electrons that I was allowed to use. And so now I'm going to look at this structure and ask, is everybody happy? No, who's not happy? Carbon. So again, I'm going to rearrange what's on the page here. I'm going to take this pair of electrons from that nitrogen and bring it down to form a bonding pair. And now is everybody happy? No. So what am I going to do? Play the same game again. All right, I'm going to take another pair of electrons and bring it down to form a covalent bond. Okay? And now everybody is happy. My carbon in the middle has 2, 4, 6, 8. And my nitrogen has 2, 4, 6, 8. All right? So if we followed all of our rules and we still have elements that have not, that don't have a complete octet, you're going to start rearranging what's already on the page, creating these higher order bonds. Okay, we call this a double bond where we got 2 covalent bonds. And we call this a triple bond compared to just a regular old single bond. Cool. All right. We're going to stop there so that we can get started on our lab practical a little early. All right. I'm going to